Hello, welcome to Electronic Systems Design. In the last few lectures, we were discussing about the PCB, what is a printed circuit board, and where we make all the circuits to make a complete electronic system. And then we discussed about the interconnecting wires. So, these are the wires, or I would say the tracks, which we lay down on the PCB or a substrate. This substrate can be a PCB, can be a like any other fancy substrate for high power, high frequency applications such as Rogers, or it can be a silicon substrate. So, depending upon the requirement, we make these tracks to connect one component to another component. So, these are the interconnecting wires. Next, we are going to talk about the electronic circuits, or what circuit we make using the devices, the electronic devices. It can be active device or a passive device. So, in this lecture, we are going to talk about the inverters, or more specifically the CMOS inverters. What is a CMOS inverter? The first word is CMOS, which is complementary metal oxide semiconductor. So, the word complementary comes in because we use two types of devices in this inverter, and these two devices are complementary to each other. For example, we use a PMOS device and an NMOS device, and these two devices are complementary to each other. So, we say that this is a CMOS process or CMOS technology, or a CMOS inverter we are going to make. So, in a CMOS inverter, we are going to use a PMOS as well as an NMOS, both of the device. So, we call it CMOS inverter. So, we are going to talk about what is a CMOS inverter and how does it work, what are the various options to improve the performance of this CMOS inverter. The first question is, why do we want to study CMOS inverter? The answer is, in most of the circuits, in almost all the ICs, this CMOS inverter is the main circuit which we use in almost all the circuits. So, this CMOS inverter is the nucleus of ICs. In everywhere it is present. The next thing is, the same analysis whatever we study in terms of CMOS inverter, the same study and same analysis we can extend to any other circuits. For example, we are talking about NAND gate, NOR gate, even the other complex circuitries, adders, subtractors, full adders. So, the same analysis what we perform on the inverter, that can be extended to other circuit as well. So, it is important to study the performance of a CMOS inverter, and the same analysis we extend to other circuits. And while studying this CMOS inverter, we will focus on multiple parameters which are crucial for our electronic systems. The first one is the cost. Cost is generally in terms of area and the complexity of the system. It is not the money cost, it is actually the cost which incurred due to the area it occupies on silicon or on the PCB. So, one parameter is the cost. The second parameter is how robust your electronic system is. So, that depends on multiple factors. For example, how much steady state leakage current is there. So, that is a power which is burning all the time in the circuit. So, that also dictates your reliability of your system. Third parameter is the performance, how fast my inverter is switching. So, if my inverter is switching very fast, it means my circuit can operate at higher and higher frequencies. And to support, like nowadays we have so many applications running around on these electronic systems, we want faster and faster systems. So, performance of electronic circuits is important because that is the circuit which is handling all these high speed applications. And the other one is the energy efficiency, how energy efficient your inverter is or any other system, because most of the electronic systems are operated on battery, and battery has limited amount of energy available in it. So we need to very judiciously burn the power so that we don't run out of power from the battery. So these are some of the parameters which we are going to see while we discuss about the CMOS inverter. So let's start. The CMOS inverter. So as we explained, this CMOS, it includes both of the devices, PMOS and NMOS. Both of these devices are used. So the basic structure of a CMOS inverter is something like this. We have a power supply which is VDD. From this supply we connect a PMOS device. This is a PMOS device, and on the bottom we connect a NMOS device. And on the bottom we have a ground. This is your NMOS device, and the gate of these PMOS and NMOS are connected together. Let's call this terminal as input, or the voltage here is V in, and these drain terminals which are connected for PMOS and NMOS, this terminal we call it the V out, or the output terminal, and generally at this terminal we connect a capacitor, that is a load capacitor. So this is the basic structure of a CMOS inverter. This load capacitance, let's call it CL. This is your PMOS, and this is your NMOS. And why do we study the CMOS inverter? This is the nucleus of ICs. This is omnipresent in almost all of the electronic circuits. This analysis can be extended to study more complex logic gates. Complex gates such as NAND gate, NOR gate, etc. So this inverter is present almost in all the ICs, and we study this CMOS inverter for multiple factors. The very first one is the cost. So the cost is in terms of area and the complexity of the circuit. The second is the robustness. This is measured in terms of static or steady state behavior. The third is performance. This is measured in terms of dynamic or the transient response. And the fourth parameter is energy efficiency. This is measured in terms of how much the energy is consumed by the circuit. So these are some parameters, for example, cost, robustness, performance and energy efficiency, which dictates which circuit we want to use on ICs, on the electronic systems. So this is the basics about inverter. We have PMOS and NMOS, both of the device present in the circuit, and we connect it like this. We join the drain of both of the devices together, PMOS and NMOS, and we call that terminal as output terminal Vout, and we connect the gate together of both PMOS and NMOS and call it the input terminal, where we apply the signal. We apply a digital pulse at the input and we watch at the output Vout. So this is CMOS inverter. Let's see how a CMOS inverter look at the silicon level, because right now what we draw is just the schematic, which is a symbolic view of an inverter. This is how we understand a device PMOS and NMOS. However, in actual practice, when we are going to fabricate on silicon, this is not the inverter look like or the device look like. In substrate or the silicon, we look from the top, which is something called a layout of the MOSFET. Layout is nothing but the collection of multiple type of layers which we fabricate on silicon. So we draw the layout, which is the graphical view or graphical representation of the same devices which we draw on schematic. Schematic is the symbolic view which we just draw. So let's see how a layout look like for a inverter. So let's draw the CMOS inverter again. So as we draw last slide, we have a inverter something like this. We have a supply VDD, we connect a PMOS, and we have an NMOS, we join the drain together. This is the V out terminal, this is the input terminal. This is our PMOS, this is NMOS. So we connect it like this. For the NMOS, we have source connected to ground, the gate is here and the drain is on the top. Similarly, for a PMOS, we connect in such a way that the source is connected to VDD here, gate is here and the drain is on the bottom. So if we see, both the drain of these devices are connected together at the terminal V out. So let's see how a layout look like for this CMOS inverter. This is the pictorial view of the layout. So here we call it the schematic, which we draw in software, and this is called the layout. So if we see closely here, this is the input node where we have a junction which is input node, and this is connected to both PMOS and NMOS. This is the PMOS region where we have a separate well which is called N well, because PMOS is fabricated always in the N well. So this is a complete well in which PMOS devices are made, and rest of the surface is P substrate where NMOS we can make it anywhere. So this is our NMOS. We need not to have a separate well for it. So this is N well device, and this is PMOS device, this is NMOS device. Now if we see, this red is the poly or the polysilicon which runs from this input node to both of the device as a gate. So this terminal we are looking at here is this in terminal, and this poly is this connection going to both of the as a gate. So this poly act as a gate. This region is gate of PMOS device, and this bottom region, this is dotted region, this is the gate of NMOS, and one side of this is source is connected to VDD. So this is your VDD line and your source is connected to this. So this is your source vias, and on the other side of this, in between we have this gate, and on the other side we have the drain. So these are drain connections. These are for PMOS. Similarly for NMOS, if we see, this is the ground line. Connected to this we have source of NMOS. So this is all source terminals, this poly act as a gate, and on the other side we have these drain connections. So this is the drain of NMOS. Now we see that both of the drains are connected, and we call that node as output node. So you see this drain connection is connected through this metal line, and we call it the output node. So here we can see this metal 1. So this output or the drain of both of these transistors, these are connected through metal lines, and metal is generally shown as blue color in the layout. So this node, which is output node, is shown as the metal 1. Similarly, if we see the VDD supply, these rails, VDD rails and the ground rails, these are also made up of blue lines. It means these are the metal lines which carries the voltage VDD and ground to the circuit. That's why these are shown as blue color. Poly is generally shown as red color. So this is the typical layout of a CMOS inverter, where we have PMOS device as well as the NMOS device. Now let's see, when we connect these two, this PMOS, this CMOS inverter with another CMOS inverter, how does a layout look like? Because in actual circuit we have to connect multiple circuits together to make a complete system. So we have to join these inverter to another inverter or to another NAND NOR gate or any other circuit. So that time we need to change slightly in the layout so that we can connect it efficiently to the other circuit. So let's see that connection. So let's discuss the case of two inverters. So let's draw the schematic where two inverters are connected together. So we have a common rail which is supplying power to all the circuits. First we have first inverter, and the output of this first inverter goes to the input of second inverter. So let's draw the second inverter now. So the output of first one is connected to the input of second inverter, and the output of second goes out as a separate terminal. On the top we have this VDD supply, and on the bottom we have GND supply or the ground supply. So now we want to make the layout of this inverter. So the one thing to note is these supply lines VDD is shared among all the circuits. So here we can see this is a single line of VDD which is going to first inverter as well as the second inverter. Similarly, the ground supply, which is a single rail, is connected to both of the ground of both of the inverters. So these VDD and GND, these are the rails which carries all the current for all the circuits. So we need to make these VDD and ground rails very thick so that they can carry that much of current to power up all the circuits. So let's see how a layout look like for this. So this is the typical layout of this inverter chain. This is the schematic. And this is the layout. So as we can see, these are the VDD supply rails, and this is the GND supply rail, and we can see these are quite thick compared to the metal we use. For example, here this thickness is very small compared to the thickness we have of these supply rails. This, let's say this is capital W and this is small w. So this, we can see the VDD and GND supply rails are very much thick in size so that they can provide current to all the devices. So the current comes in, let's say from here, it goes here to first inverter as well as to the second inverter here. Now the first block is the first inverter. We have this input terminal, let's mark this as input, and then we have an intermediate node here which is connecting output of first to input of second. This INT node is here where we are connecting the drain of the first inverter to the source of, to the gate of the second one. This is the gate of second inverter. This is the input intermediate node, and this is the output node. So this is how a layout of two inverters look like when we connect them together. And one more thing to note here, this well is not individual well of all PMOS ICs or PMOS devices. We have a common well. This well is not ending here, but it is actually extended up to here, and all the PMOS devices, if we use 2 PMOS, 10 PMOS or 20 PMOS, they are all sharing a single well. So this is the N well, in which we make all the PMOS devices. So let's say we call it PMOS 1 and PMOS 2, then this is our PMOS 1 and PMOS 2. And here if we have this NMOS 1 and NMOS 2, this is our NMOS 1 and NMOS 2. So this is how a complete layout of inverter chain or two inverters connected together, it is how it look like. So this is the view of layout. Layout is nothing but the graphical representation of schematic. This is how the actual layers we collect together, and this is how we are going to fabricate it on the actual silicon which comes out of the foundry. So now let's discuss about the CMOS inverter, how a CMOS inverter works. When we apply a signal, how the CMOS inverter actually works. So let's discuss when we apply a static signal on inverter, how the CMOS inverter look like. So let's first draw a CMOS inverter. So this is the CMOS inverter. Now when we apply the input as VDD or the high input at the input terminal, then the circuit, equivalent circuit, look like something like this. This is VDD, and when we apply a high input, the actual PMOS, this is off, and the NMOS is actually represented by a simple resistance. This resistance value, let's say this is Rn, the resistance of NMOS, and this is our output as at node out. So when we apply a high signal, V in is VDD, then PMOS is off. So this is shown by this open symbol, and NMOS is replaced by a resistor, and V out is the node which is going to be discharged through this Rn. However, if we apply a V input low, let's say V in equal to 0 or ground, then the equivalent circuit looks something like this. In case of 0 at gate, NMOS turns off. So we have now an NMOS which is now open, and PMOS is now replaced by a resistor. This is the output node, and this resistance is, let's say, Rp. Now this switch is off. So when we apply input as high, PMOS is off, so there is no current coming from the top VDD, only current which can go from output to ground through Rn. In second case, when we apply V in as 0, the current will come from VDD to the output node through this Rp, and the current cannot go from output to ground because the NMOS is off. So there are few points we can notice for this. The low and high output levels equals to VDD and ground. This is the CMOS inverter, its ratioless design. It means the logic levels do not depend on device sizes. V out, the output node, is always connected to the low impedance path, which is VDD or ground. The input impedance is very high. And we can say there is no static power dissipation. So here we see the equivalent circuit of an inverter, where we have PMOS off in one case and the NMOS off in another case. So if we see it closely, the output high and output low is nothing but at the supply level or at the ground. So we, in one case, in the first case, let's call it the case 1. In first case, we have output node connected to ground through Rn. So no matter what, at some point V output node will be discharged to ground. It means the output node is connected to the ground or the voltage is 0. In another case, the output is connected to always VDD. It means this output node will be having a complete high value, which is VDD. So the low and high levels at V out, the output node, is either VDD or GND. There is no voltage in between of this voltage. In the steady state value, either it is 0 or it is high. So we have only two values at the output. It increases the kind of noise margin. The second is, it is a ratioless design. What is a ratioless design means? No matter what the input is, the output is always 0 or 1. In ratioed design, we have simply a resistance on the top, which can change the value at the output to an intermediate value as well. But here the upper device or the lower device is completely off. It means the output will achieve a complete high or a complete low. It does not depend on the ratio or the sizing of PMOS and NMOS. So this is a ratioless design. Output is always connected to either to VDD or GND, as we discussed. The input impedance is very high, which is very important factor for a CMOS inverter. If we see the input, when the signal comes in from other device to this inverter, the input node is connected only to gate of those devices, PMOS and NMOS, and gate is a very high insulator. It does not draw any current. So it offers a very high impedance to the source which is generating the signal. If the inverter does not draw any current, it means we can connect multiple inverters together with the same source and they all can function. However, in another case, if we have an inverter which draws the current, then it is difficult to connect multiple inverter because they all will be drawing some current which can affect the functioning of the source. Here in the CMOS inverter, we have very high impedance at the gate, and there is no static power dissipation because in both of the cases, if we see, we have either PMOS off or NMOS off. In any of the cases, there is no direct current flowing from VDD to ground. So, there is no static power dissipation in this CMOS inverter. There is no burning of power when the signal is not transitioning. So, if the signal is static, there is no current consumption in the CMOS inverter. So, these are some of the points which we can see from DC analysis: low and high levels, this is ratioless, input impedance is very high, and no static power dissipation. So, now let us discuss what is the voltage transfer characteristic of a CMOS inverter look like. We can draw the inverter again for ease of understanding. We have this inverter, this is V in and V out. We have this VDD and GND. Now, let us draw the voltage transfer characteristic, which is nothing but V out versus V in. So, the y axis is V out and x axis is V in. So, at very low voltages, for example, let us say we mark it the x axis. So, at very low V input are almost at 0 level, we are increasing the input from 0 to high at V in. At 0 level, this NMOS is off and a PMOS is completely on and is in resistive region. So, we can say at V input 0, we are somewhere here. The output is high because the V out is connected to VDD through PMOS. At this point, our NMOS is off and our PMOS is in resistive region. Why this is in resistive region? Because the gate to source voltage is almost equal to the drain to source voltage is very high. The drain to source voltage is very low because V output is almost equal to VDD. So, the PMOS is resistive. This is complete characteristic. When we start increasing this V in, what will happen? At some point, my NMOS will turn on. At this point, let's say NMOS turns on, and when it turns on in saturation region, and PMOS is still in resistive region. NMOS, when it turns on at saturation region, because and in starting this V out will be equal to VDD. So, drain to source voltage will be very high compared to VGS minus VT. So, NMOS will turn on in saturation region. At midpoint of the input, NMOS will be in saturation and the PMOS will also be in saturation, and as we keep on increasing the input signal, at some point NMOS will enter into the resistive region, because now drain to source voltage is decreasing. It means VDS is decreasing, so it is no longer more than VGS minus VT. So, NMOS will enter into resistive region, PMOS will enter into saturation region, because PMOS drain to source voltage is keep on increasing. So, it will enter where VDS is greater than VGS minus VT. So, this is the point where PMOS enters into saturation, and finally at higher values our NMOS will be in resistive region and PMOS will be off. So, this is the typical voltage transfer characteristic of a inverter. At low value, at input low, output is high, and at input high, the output is low. And in between, the transition happens something like this. We have a slowly going curve from top to bottom, and these are various sections where the PMOS and NMOS changes their region of operation. So, this is how a VTC or voltage transfer characteristic of a inverter look like. So, this is the characteristic of an inverter in normal condition, when we just make a PMOS and NMOS connected together, make an inverter, and this is how we get the voltage transfer characteristic. Most of the time there are so many factors which can affect the VTC or the voltage transfer characteristic of inverter. For example, the first one is the process variation. When we fabricate these PMOS and NMOS, sometimes the PMOS is not as good as we wanted it to be, or sometimes the NMOS is not as good as we wanted it to be. So, because of the change in the performance of PMOS or NMOS, this voltage transfer characteristics can also change, because the voltage what we are drawing, V out versus V in, the actual voltage depends on how much is the strength of PMOS compared to NMOS, because at some point the NMOS is in saturation, PMOS is in resistive region. So, there is a fight in between these two devices to pull the node up or down, the output node. So, that fight actually depends on how good a PMOS or an NMOS is. So, based on the sizing or based on the process variation, this VTC voltage transfer characteristics can change. So let's see how the VTC look like if we have process variation. So the impact of process variation. This is V out, this is V in. Let's draw the first VTC. So in normal case, let's say the VTC looks something like this. This is the normal VTC. Now let's say we have, because of the process variation, we get a good PMOS and a bad NMOS. So the VTC transfer characteristics look like something like this. So this is how VTC look like for a good PMOS and a bad NMOS. And this good and bad is happening because of the slight process variation which can happen during the fabrication. Let's take the second case where we have a good NMOS and bad PMOS, which is reverse of this case. In that case, we will have characteristics something like this. This VTC will shift towards the left. This is the case we have a bad PMOS and a good NMOS. And what is this good and bad devices? The good device generally has smaller gate oxide thickness. So this is the impact of process variation. Process variation is something when we are fabricating the device, because of the inherent change in the process, there can be some misalignment, or we can say changes in the device compared to what we target, that leads to process variation. Because of this process variation, there is a good PMOS or a bad PMOS, a good NMOS or a bad NMOS. Because of this change in the process of PMOS and NMOS, this VTC, or the voltage transfer characteristic, it can shift left, right or left depending upon PMOS is good or NMOS is good. When we say good device, it means the current driving capability of that device is higher compared to a bad device. So, this happens because of these few reasons. The good device generally has smaller gate oxide thickness. If we have smaller gate oxide thickness, generally the current produced by the device is higher. So, there is, when we fabricate this TOX, which is generally in nanometer range, 5 nanometer or 6 nanometer, when we fabricate this very thin gate oxides, because of some change slightly somewhere, this thickness can be higher or lower. So, if because of process variation the thickness is smaller, then we have a good device, or you can say the faster device. The other one is the smaller LG. So, because of some process variation, the gate length comes out to be smaller, let us say 5 or 10% smaller than what we target. So, that device act like a fast device. We should not say good device, but it is a faster device. This is not the intended one. So, because of these faster and slower devices, this VTC is changing. So, we have fast device if we have smaller LG, or higher W if we have higher width, the current driving capability of device is higher. Similarly, if the VT, the threshold voltage of the MOSFET is lower, then also the current will be higher. So, if we have smaller VTH, then also our MOSFET will be faster, or we can say this is good device. So, depending upon process variation, now the performance of the circuit is changing. We change the device PMOS or NMOS intentionally or unintentionally. Because of these changes, the performance of our circuit, which is complete inverter circuit, this VTC is actually shifting, and we can change this shift up to our requirement. If we want a very kind of VTC characteristic toward the left, we will go for a very fast NMOS and a very slow PMOS, so that VTC is shifted towards the left or towards the right if we have a fast PMOS or a slower NMOS. So, this is the DC characteristics of an inverter. So, this is all for today. Next we will discuss the transient characteristics of an inverter. Thank you.